Well, guys, so first of all, I think Emily bought some munchkins for you, right? So it's just so that at least it's going to be a little bit sweet, our deltas and epsilons and everything that we do today. I actually took Liz's advice. I figured like very long time ago, why not? I'll feed you, Russian candy, right? So there are a few types. You can eat them, and I mean, I usually tell some of my students, Calc 1 students usually, on April's, but it was on April. I'll tell them some of those candies, what do they mean. Yeah, Russian market everywhere, or what you call, Russian, like members of the subjects of the big Russian Empire, right? So yeah, just pick whatever, just a few of those.
Thank you.
There are different sorts.
Is that chocolate?
I don't know, right?
It's super authentic.
Do you know what that means?
Yeah, I can tell you what it means if you want to. One of them says, "Don't eat me." Right? One of them might have been accidentally. Right?
This is Russian. Cool. Is this like a block of cheese or something?
What?
It's like a block of cheese. There's like a cow in it.
Yes, there is one with a cow. There is one other with a bird. The bird is the more interesting one. You haven't looked enough.
But the one with the bear.
The one with the bear is Russia symbol, right? It's called I think Mishka Kasalapi, right?
Oh, clearly, yeah.
It's a famous, yes.
Looks like a Kit Kat bar.
Oh, that's
Yeah, it's pretty much like a Russian Kit Kat bar.
Gotcha.
Oh, we missed it. We missed it.
Last I missed.
Right. I thought okay.
It's okay, I watched your video.
You're actually you're just handing out awards for perfect
I don't deserve this. So I'll have to see.
That's your own.
I got that Russian candy.
These are things that circulating straight up. What?
Good one now.
Which one's the best?
I don't know. There is one that since the time I can't right now.
I know.
Anybody wants this?
I'll take a third. Sure.
No?
Oh, there's brandy.
Make sure yeah? Make sure you pick the one with the bird, right? I'll tell you why. Bird, right? There's one, I guess, right? He knows. Right. I didn't want to repeat this, but actually at Brooklyn College I had a student that made me want to repeat this. I'll tell you why.
Is that a bird?
Yeah, that's the bird. That's
a bird.
Yes, you see there is a bird here.
Oh.
That's very important.
Yeah, I think I just got it out there.
Still a one.
How many of you know about the bird?
I know of birds.
The Russian bird?
The Russian bird, you know? Okay, good. So I feel only bad that Matthew knows, right? But all right, I guess if you don't know, so I'll tell you.
Yeah, I think there's only cows.
No, there are also birds.
All right.
Cows is what you become when you eat this too much. All right, so you see, so I'm walking actually with my brother there to Brooklyn College, and then there is this guy. He catches up to me and says, "So tell me, is it true?" And what's true? Apparently, his wife years before has taken my class, right? And she still wonders. I mean, one thing that really is bothering her about this calculus is whether it's true that that what I do is what I do, right? And I explained to them why am I at times too very angry, especially at Calc 1. So there is a candy, if you look at it, you should have had it. It looks like it's a block, and on top of it you have a picture, something like this. Right?
Whoa.
Though you have, so you see, actually, I used to paint it some years ago, right? Do you have a picture like this or something like this? Have you ever seen? So make sure everybody has a candy like this, right? So
Candy bag, I got it.
you see, just make sure that you have it, and then take a bite out of it, and then. So what was she wondering about? There are a lot of people that major in biology, so I always ask them two questions. First of all, tomatoes, vegetables or fruit?
Fruit.
Fruit, right? So okay, good, you're smart. Tomatoes are fruit, right? What about birds? Mammals or not mammals? You see, you think not mammals, right? But that's where you are very, okay, here you go. One person knows that they are mammals. How do you know they are mammals?
Wikipedia.
Huh?
Wikipedia?
You can do what?
Wikipedia. I looked at online.
Wikipedia.
I'm pretty sure I looked at online. Yeah.
Oh, maybe you have, right? Maybe you have, but basically a lot of Americans don't know that birds are mammals. So,
Why? You have
They're
eggs.
like avians. I thought we were talking
well, they're avian mammals. Why not?
avian mammals. I thought they were vertebrates.
Wait, why is that mammal?
Hey, we're gonna ignore the one of you.
Let's note to all persons of keen perception that birds are in fact mammals. The milk these animals so diligently produce is often squandered on the pavement. And it took the entrepreneurial spirit of some Eastern European denizens, which could only arise from the resigned indifference brought on by harsh, cold climates, to first attempt the milking of an ornithoid. The most successful of those early attempts were on the columbiform, or pigeon. It is speculated that the first established bird milkery was located on the outskirts of the small village of Nova Svarsava. Here is the earliest known photograph of a bird milk processing facility in Globa Grad. Skipping ahead several centuries, we arrive at a crucial point in our story, where immigrants of Polish and Belarusian descent carried over their traditions into New York, specifically Brooklyn, and even more specifically, the intersection of 13th Avenue and Day Hill Road, where remains the factory to this very day, on the second floor of a paper mill processing facility.
Right?
Wait,
So pretty much. So let's see. At least one way I understood that I had very big influence on my calculus students. Right? So years, she thought about my work. So what I asked is basically what I explained to them is, okay, here's a bird. How do you know it's a mammal? Well, you can milk it, right? And what you eat, the candy that you're eating, it's called bird's milk. You understand?
wait, so this is milk from birds?
Yes, that's milk from birds.
Ew, no.
This is some kind of satire, right?
Yeah.
Well, I see. At least maybe then you remember this class, right?
Wait, is this actually happening?
Huh?
Technically a mammal?
Well, tell me about it, right? Here you go, right? Everything you can milk is a mammal, sure.
That's not.
I guess men are not.
What other? I mean, what other operating definition do you have for a mammal? Huh?
I mean, like reptile.
No.
If you can milk a reptile, then it's a mammal. But have you tried milking a reptile?
I mean, like the only mammals that like lay eggs are like platypuses.
I thought you
It's
said
Oh, in my biology class.
You see, I mean, I haven't done it in a long time. I figured, you know. Well, what is it? When was it? Like 2014, the first time I explained it, I think.
Wait, so a bird's actually a mammal?
So you see, here we have a good discussion today.
Try some bird's milk and find out.
Yeah, try it. Did you eat it? Eat it.
well, if you can't prove that it's not a mammal, then it must be a mammal.
Exactly. You try it.
Only from birds.
All right. So let's do our last integration.
But the ingredients don't really help out too much.
Do you want to read the ingredients? Bird's milk and some sugar.
All right, thank you.
Yeah, guys. But you see, I had a legacy. It was like the husband of somebody who took my classes years ago, right?
Remember nothing about the math.
No. That's what I said. You see, at least, yes, at least.
No, I have to Google this.
All right.
Wait, Harrison, which one do you think it is? Mammal or not mammal?
I think it's not a mammal.
Yeah, how much you want to bet?
I'm just convinced, after the scene where the bird pooped on the kid's face, I'm convinced that video was satire.
The bird poop is the milk. That's,
Is the milk.
that's
And
the joke.
Yeah.
I mean, I said at least, you see, if you're not going to remember me for the math, at least you remember me for the bird crop, right?
First, it's a class.
Oh, it's not a mammal?
No, it's mammal, bird, fish, reptile, amphibian.
Yeah, so.
Oh, okay, cool.
All right.
Hey.
Good. So integrators of bounded variation. So we assume that alpha belongs to the space of bounded variations on AB. So alpha no longer is monotone. Monotone, maybe I should say, maybe it is monotone, so no longer monotone by default. So we need a new definition of the integral, because if alpha is not monotone, basically if we have P a subset of Q, partitions of the interval AB, we no longer know by default that the upper sum over the partition P of F. By the way, what should be its relationship in general with the upper sum of the partition over Q? If you remember, right? If alpha were monotone, those upper sums are directly related. Yeah, so which one is bigger, which one is smaller? Q is bigger or smaller? Q is a refinement. So what happens to upper sums when you refine?
They get smaller.
Smaller. I hear bigger. It's smaller. Smaller. They get smaller. But we no longer know that because the partition is, because of alpha. It's not necessarily a monotone function. Right? Or that lower sum of F P. What usually is the relationship with the sum over Q? I mean, again, smaller. Which one smaller? So this guy compared to this one. This one smaller or bigger? Left smaller than right. Okay. Lower sums grow, upper sums fall down. Right? No matter. It's the last lesson. You don't need it anymore. Right? So given partition P, we are going to try to make a new definition for the Riemann sum, for the Riemann-Stieltjes sum. So this is x0, x1, xn. We are going to let T be a collection of points, T1 through T sub n. And this denotes an arbitrary selection. Of points from AB with Tk belonging to the interval xk minus 1 to xk. And we then call so the summation for F, for the partition P, with the points T, this is just the sum k equal 1 to n of F T sub k times, in parentheses, alpha x sub k minus alpha x sub k minus 1. So this sum is what you were introduced to in Calc 1, right? That's what you were roughly doing, where usually Tk was picked to be the either left endpoint or right endpoint or midpoint. But in general, we can consider a sum where this is some arbitrary collection of points at which you construct the height of your rectangle. So this is called a Riemann-Stieltjes sum. For F. Okay? So what's the definition of integrability? So we say that F is Riemann-Stieltjes integrable with respect to alpha And that would mean that f is in the space R sub alpha A to B. If and only if there exists a number and this number is some I, that's the integral. It's a real number such that for every epsilon bigger than 0, there is a partition P star for which S F P T minus I is less than epsilon for all refinements. P that contain P star and all selections T. Does it make sense, right? This is actually almost what you usually think of Riemann sum. So what you have is you have small enough rectangles so that if you vary those rectangles, you vary them by changing the t. The area does not change much, right? And that's what it precisely means. So it looks like a very difficult condition to test, perhaps. But several things immediately are apparent when you look at it. So it's immediately apparent with this definition, more so than with the upper sum, lower sum definition, that the integral is linear. So remark, actually before even that, let's first notice that such a number I must be unique. Remark, if such I exists, it must be unique. And again, it's actually almost obvious why, but let me just explain nonetheless. So if J is another such number, what we can do is we can then let P star and Q star be partitions such that both conditions happen. So such that if I take S of F P T and I subtract I get less than epsilon over 2. And if I take S of F Q T and I subtract J, I get that the difference is less than epsilon over 2 whenever P contains P star and Q contains Q star. So what do I do then? You see what happens? I mean, by this definition, I mean, suppose I found for each epsilon over 2, I can find partitions P star and Q star such that both conditions are satisfied. I want to show that it implies that I and J are the same number. Okay? So what we can then do is we can say that let's measure the distance between I and j. So I minus j is less than or equal to I minus s. And I can take union of p and q. I can make a refinement that will make it a partition that contains p star and a partition that contains q star at the same time. So I will have s f p union q t. By the way, this t changes, of course, right? This t will be, well, I mean, you can just decide it would not be the same t as we have here. This t depends on f. This t depends on q. I don't know, maybe, I guess I don't want to distinguish them too much. Just gets, but you understand that technically I'm abusing t. So what you have is that this plus S F P union Q T minus J. Now by hypothesis, this is smaller than epsilon over 2, this is smaller than epsilon over 2. The entire thing is smaller than epsilon, and epsilon is arbitrary. Since epsilon is arbitrary, what?
The siren was just really
Bad
funny.
inputs.
I don't know.
I is equal to J. All right, so the other very obvious thing is that it's easy to see that the integral is linear. Well, why is it easy to see that? Well, we can just look at the Riemann sum. So if I take S of CF plus DG over some partition P with points T, that's clearly equal to C S F P T, because it's just really a sum, right? It's just a sum plus D S G P T. And our assumption is that integral of f and the integral of g exist, right? So then if I know integral of f and integral g exists, so there is a number I for f, there is a number j for g. So we can easily come up with the names, right? So the implication is that absolute value of S CF plus DG over the partition P minus the unique number that works for f. It's written as the integral from a to b f d alpha. So this is our I. This is the unique number that we showed that such number is unique, so we can denote it by this sum. And there is a corresponding unique number for G. And when we look at this, we can apply triangle inequality. And triangle inequality tells us absolute value of C, difference between the sum F, P, T, and the integral of f plus absolute value of d, the difference of the sum s g minus the integral from a to b g d alpha. So what does this imply? This number decreases to 0, this number decreases to 0 as we refine the partition. So hence, the integral ab cf plus dg is equal to c integral abf d alpha plus d integral abg d alpha. All right. So that concludes with the easy results. The next result is you can actually come up with it on your own, integration by parts. So the result tells us that if I look at some function f, it belongs to the space of integrable functions over alpha if and only if alpha belongs to the space of integrable functions over f. And in either case, we have that the integral from a to b of f d alpha plus the integral from a to b of alpha df, it's equal to f of b alpha of b minus f of a alpha of a. Proof. So suppose that f is integrable over alpha. So what does it mean? It means that we can pick a partition P star such that the sum with respect to alpha of f p t minus the integral is less than epsilon. And that will be true for all partitions that refine P star and all selections of points T. Make sense? So the fact that f is integrable with respect to alpha means that I can construct a sum of rectangles where the partition is so fine that if I select various points T within this partition, that will not change much the sum of the integral, the sum of the rectangles. Okay. So then I want to estimate what's the corresponding sum for alpha. So what we do is consider the sum sub f of alpha pt. So what is that? this is where I use the same partition P, I use the same points T, but where I reverse. The rows of the width of the rectangles are built out of F, and the heights are built out of alpha, right? So that would be summation k equal 1 to n of alpha tk times f of xk minus f of xk minus 1. So that's the corresponding sum for f, and I want to relate it to the sum for alpha. How are they related? So you look at the sum, you just separate, so you multiply this alpha times this f, and you can just change the index so that it also runs from k to basically when it's not k minus 1, where it runs through k. So that becomes, first guy is k equal 1 to n, alpha tk f of xk, minus the second guy, I change the meaning of k, so I'll start k from 0 and to n minus 1. And that would be alpha t k plus 1 So you understood what I did, right? I just changed so that it's not k minus 1 but k, and therefore I had to change the bounds of summation. And now I want to combine them. So this goes from 0 to n minus 1. This needs a 0, and this needs an n, right? So what I do is I introduce those points, and I subtract them. So this is, you can see that this is alpha tk plus 1, so it looks like delta alpha. Yeah, somebody has a better party. You want to join, right? Maybe they have better food.
Sorry, Professor. Oh,
Yes.
So for the first line, is that always true? Like f belongs to the Riemann integral if only alpha belongs to that?
Yes, it's always true. But again, we're considering functions of bounded variation. So Riemann-Stieltjes integral, this alpha is a function of bounded variation. Okay? And that would force f to be a function of bounded variation. Okay? So the idea is, again, we have one sum. It's actually the if and only if is immediate because those two sums are related. What you're doing is, without using derivatives, without using the product rule, you're actually constructing a formula that is exactly like integration by parts from calculus 2. Okay? So you see, by doing this, look what we had. Here we had delta f, that's df, right? And here, by reconstructing, we have minus, you look at it, minus delta alpha. You see, we have f of xk times minus delta alpha. So what we do, we just regroup, factor the minus 1. So you factor this minus 1. You have the summation k equals 0 to n of f of xk times alpha tk plus 1 minus alpha tk. And we had to introduce 2 points, right? We introduced a point at 0 and we introduced a point n. So, sorry?
Times alpha?
So we need to add.
Aren't we missing a factor of alpha? There.
No. We group it together. We have this and that we group together. But you see, this one starts from 1 to n, and this one starts from 0 to n minus 1. So I need to introduce. I introduced, in order to this to collapse this into a one sum, I introduced one term here, the nth term here, which because if introducing it means it's subtracted, I need to add it. So this is plus and plus f of x sub n, right? X sub n times alpha, and I didn't yet have it. I'll explain what is that tn plus 1, right? Because I need k equal to n. Okay, and then I also to this guy I added, so I need to subtract. I added f of x0 times alpha of t sub 0. Okay. Now, what is this? So that you can see what I added, I actually am going to draw it on the number line, right? We have several types of points. We have points x's and we have points t's. So we have the point, I'll put it, this is point A, this is point B, and then we have A is the same as x0, okay? B is the same as x sub n, correct? And then I have x1, x2, etc. Somewhere over here is xn minus 1. I have those points. Okay. What other points I have? I have the points t. So when I began the summation, when I was looking at this sum here, I only had t1 all the way to t sub n. Where were those points? Those points were somewhere. This is t1, I don't know, somewhere in the first interval is t1, somewhere in the second interval is t2, somewhere here is t sub n. Okay? Now I created new points, right? I created t sub n plus 1, and I created t sub 0. What's the nice place to put t sub n plus 1 and t sub 0? So x0 will be t0. And xn will also be tn plus 1. OB. Okay, so that's the picture that you can refer to in what we're doing. So you see, what partition did we obtain here? This here is just minus. So this sum that I have here, it's what? It's minus s sub sub alpha, because you see we have delta alpha, it's this, right? It's s sub alpha of some sort of reversal. So you see I'm using xk's as t, so it's of the function f, and with the exception of those points that I added, I would say this is, instead of the partition p, I'm using t, and instead of the points t, I'm using p. Well, t is a little bit modified, right? I modified it by introducing t0 and introducing tn plus 1. But aside from that, this is what happened. So you see, we began with a sum alpha p t. We end up with, so this is s sub f. We ended up s sub alpha f, p and t are reversed. And we have plus f of b alpha of b minus f of a alpha of a, and we will denote this new partition, right? So that there is no confusion. We'll say this is minus s sub alpha f P prime T prime. Okay? Now we need to refine this partition, you see? So we need to, we know that, where did I put it there? We know that this sum is essentially this sum, right? But I want this new partition T prime is not related directly to the old partition P because it's using the points T. See, this new partition is using the points T, but it has to be a refinement of the points X. Okay, so we can do the following refinement. So we can say S sub alpha of F P prime T prime. This is summation k equal to 0 to n of f of xk alpha t sub k plus 1 minus alpha t sub k. What you can do with the sum, you can write it as the sum k equals 0 to n f of xk alpha tk plus 1 minus alpha xk. So I break this into two sums, plus f of xk alpha xk minus alpha tk. And this now represents the sum S sub alpha of f, a new partition P double prime, and new choice of points T double prime. You see what we did? We basically broke this interval so that it goes through the points x and t, x and t, x and t, x and t. So in particular, where P double prime is the collection of points x0, t1, x1, t2, etc. And T double prime, I make the choices x0, x0, x1, x1, xn, xn. Right? You see, because I make the same choice of point for when I'm here and when I'm here. So what does it imply? We have that S of f at alpha p t minus f of b alpha of b f a alpha a minus the integral ab f t alpha. This is simply the integral ab f t alpha minus s alpha f p double prime t double prime. And by hypothesis, p double prime is a refinement of p star. So and this integral exists. So this is made less than epsilon. So the conclusion is then that this alpha, you can see here, right? So this sum can be made as small as you want. So alpha has to be integrable with respect to f over the interval ab. And the integral is simply so clearly a similar argument goes the other way around. Clearly, if we assume f belongs to, so alpha belongs to RFAB, the argument is the same. So this formula actually very easy to remember. It's just integration by parts, right? That's what you do when you switch derivatives. So alpha df, f d alpha. That's what you do in Calc 2. So the corollaries of that are the following. If we have that f is in the intersection of alpha and it's integrable with respect to beta, then f belongs to R of alpha plus minus beta. So it's integrable with respect to the sum of those integrands. And the integral from a to b of f d alpha plus or minus beta, it's the integral of f d alpha plus or minus integral f d beta. The proof is fairly obvious. You just use integration by parts. So what you do is you can say that the integral a b f d alpha plus beta. I mean, even before that, I should say, if you want to justify why you can write integrals, you can say that f belongs to R alpha plus beta, let's say, if and only if alpha plus beta belongs to Rf, and that's if and only if. And we know, or maybe I said, and we know that alpha and beta separately belong to Rf. Which implies that alpha plus beta belongs to Rf, which implies that the integral from AB of f d alpha plus beta. This is just simply alpha plus beta evaluated at b minus alpha plus beta evaluated, alpha plus beta at b times f at b minus alpha plus beta at a f of a minus the integral ab alpha plus beta df. And alpha plus beta, it belongs to the integral with respect to f, so this integral makes sense. So you just use the linearity of the integral, and you see that this is the same as alpha b f of b minus alpha a f of a minus the integral ab alpha df plus beta b fb minus beta a fa minus b beta df. And each separate part simply becomes, this becomes integral ab f d alpha plus integral ab f d beta. And that's done. So corollary, if f is monotone and alpha continuous, on AB, then f is integrable with respect to alpha. So again, this is true because you can switch it around. If basically alpha is integrable with respect to f, therefore f is integrable with respect to alpha. Corollary. If alpha belongs to the space of bounded variations on AB, then every continuous function is integrable over alpha. On the other hand, if alpha belongs to the space of continuous functions, then the space of bounded variations over AB is a subset of all functions that are integrable with respect to alpha. In particular, continuous functions and functions of bounded variation are Riemann integrable. Proof. So if we assume that alpha belongs to the space of bounded variations, alpha has to be equal to beta minus gamma, where those are increasing functions. So what does it mean? It means that the space of continuous functions belongs to the space of integrable functions over beta, since every continuous function is integrable over a monotone function. And also over the other monotone function. Now, if a function is integrable with respect to beta and with respect to gamma, that means that it has to be integrable with respect to the sum of beta and gamma or the difference of beta and gamma. So that means that this intersection is contained in the space of integrable functions beta minus gamma over AB, which is in fact our alpha AB. So using integration by parts, if on the other hand we have alpha is continuous, that means that the space of bounded variations over AB. So basically what we showed is that continuous functions are integrable over bounded over any function of bounded variation. That means every function of bounded variation is integrable with respect to every continuous function. Yeah, to go into the next result, I think it would be too long, more than we have time for. Oh, you want to go to the next result?
Well, then we'll never see it.
Well, it's in the book. Did you bring your exams, guys? Everybody brought your exams? All right. I mean, if you feel a disappointment, I feel pretty much I'm saying beta, gamma, lambda, delta, epsilon, p prime, refinement, right? I mean, maybe you follow. I mean, I'm hoping you follow. But I think, am I following myself? I'm talking about alpha, beta, gamma, lambda. So I think, oh my God, the torture has to be over. Did you follow the proof? Yeah?
This is the final.
No, I didn't put it on the final. You want me to continue or continue? It's okay.
Well, I mean, you can if you want.
I can say what the result is, I guess.
Yes.
Okay, I'll tell you. I'll say the result. All right. But again, you see, it's you can look it up in Carothers. I'm just following it exactly. So. All right, so basically, first question, I suppose, what we have shown is, so we have shown that if alpha is equal to beta minus gamma, and beta gamma increasing. Okay, it follows that the intersection of integrable functions with respect to beta with the space of integrable functions with respect to gamma this is necessarily contained in the space of functions integrable with respect to beta minus gamma. You see what you do? You use integration by parts. That's the idea, right? So if a function is integrable with respect to beta and with respect to gamma, then both beta and gamma are integrable with respect to that function. And therefore, the difference of those functions is integrable with respect to that f. And then you can reverse.
Didn't we just use that result in that proof?
We did. We're always using. We're using the. Yeah. So we have this result from that proof. Correct.
Oh, okay.
All right. So we know you have inclusion. Right. The question is, does it have to be? Do they have to be equal? Is it true that alpha sub beta equal to the intersections of those spaces to this? What do you think? In other words, if a function is integrable with respect to one increasing function and the other increasing function, it will be integrable with respect to the difference of those increasing functions. But this is always the case, right? But is this the whole space? Or are there other functions that are integrable with respect to the difference of those functions, yet not integrable with respect to beta or with respect to gamma? What do you think?
Does this have anything to do with the Jordan formula?
Yes, well, that is the theorem actually, but without looking at the Jordan form tells you that every function of bounded variation can be written as a difference of two increasing functions. Right? So, is this true? The answer is huh?
Is it right there?
Yes.
For the next season.
Yes, no?
Yes.
That's not. So the answer yes. Who says yes? One person. No. The answer is no. It's not true.
Oh man.
No.
You were close.
Now, why is it not true? Take very simple example, right? So take, for example, beta equal to gamma be any increasing functions. Right. So what can you say about R0 AB, what functions are integrable with respect to the 0 function? Every function. Well, in particular, we are not allowed to pick any function. We are allowed to pick only class of bounded functions. So every bounded function is integrable. But if, for instance, beta is not continuous. So if the function beta is not continuous, you would have that not every bounded function is integrable. So not every function will be integrable with respect to beta. So the inclusion is proper. So that's a very easy example.
It's functions that share a point of discontinuity.
Precisely. So if you have an increasing function and it has a point of discontinuity, create any other function with a point of discontinuity in the same place, this function will fail to be integrable with respect to that. So you see, we have constructed an example. 0 is just trivial. Everything is integrable with respect to 0 with a very trivial integral, which is 0, right? Right, but so this shows that there is proper inclusion. So there is a theorem. Let me just write the theorem, and I guess we'll call it. Theorem tells you that it's not a simple theorem, actually. If you take alpha in the space of bounded variations on AB, and you let beta sub x to be the variational function from a to x of alpha, then you know already that beta, and we proved it some time ago, and beta minus gamma are both increasing. They are both increasing, and what would follow the space of functions integrable with respect to alpha is exactly equal to the space of functions integrable with respect to beta and with respect to beta minus alpha. That's the result. Okay? So if you do this canonical, if you have this canonical partition into two increasing functions, then the intersection of the two integrable functions will give you the full integrable space with respect to alpha. All right?
How does this differ from the other one?
How does this differ from this?
Yeah.
Well, in here I just selected, how did I partition? I took 0 and I wrote it as a difference of any two increasing functions. 0 can be written, just take one increasing function, subtract to it that same increasing function, you get 0, correct? Just pick any increasing function.
Sorry, I mean, like, I can ask you after that.
Yes, it's over, right? Forever.